right, hi everybody. Thank you for joining me on such a day with such beautiful weather. You could be outside and you're here. I hope you can enjoy it more after class. We are going to be talking about static failure theories in this lecture, which is a topic that is probably not new to you in some sense. But I do want to make sure to cover it, and then the topic after this will start getting into non-static loadings, specifically fatigue loading. The things that we've covered so far, like how to define a 3D stress state very generally, will be useful for both static and non-static loadings. And once we start talking about cyclic loading, it'll open up sort of a can of worms in terms of other things that we have to consider. So one of those is stress concentrations. Just want to give you like sort of a preview. In static loading, stress concentrations are not as important because of strain hardening. But when we have cyclic loading, fatigue loading, stress concentrations do become much more important. When you have fatigue loading, if we carry that out to like, infinity time, then you're very likely to initiate a fatigue crack. And so when a component stops being the dimensions and the surfaces that it has been designed to have, and then it has a crack, then we go into some different types of analysis. One thing that I wanted to mention is when we talk about static loading, there are basically three sort of material parameters that we've talked about so far that have controlled our failure, or in this case, just yielding, right? So in this case, I just wanted to make sure that we're on the same page. So we've had sort of, the yield stress or the yield point, right? So that is just one particular point on a stress strain curve. We pull it off and we'll use it, and we'll use it a little bit more today. And then we also had one sort of example problem, the classical pressure vessel, where we had a strength coefficient and a power law that described strain hardening behavior. And we substituted those in to talk about how the dimensions change due to plastic strains, and connected that back to the input to the system, which was the pressure inside a pressure vessel. We've also talked about Hooke's law, so we talked about the elastic modulus, E, and Poisson ratio, nu. Right. And so we'll talk about this for one more lecture, but when we start getting into cyclic stresses, we kind of open up that can of worms, right? And so now we start talking about the fracture toughness of a material. So these are all material properties terms I'm talking about here, and how that could be used as a failure criterion instead of yield stress. And that would be for like linear elastic fracture mechanics, right? Which is kind of, we still have an elastic component, but it has a crack in it. And then when we will define another stress that's lower than the yield stress, right? And that would be the fatigue limit. And we'll start talking about the fatigue limit, which is less than the yield stress and less than the ultimate stress. But we do need to include the ultimate stress or the ultimate tensile strength in our calculations along with yield stress when we start talking about fatigue and how things are loaded. So we're basically going to keep building in complexity, and this will be the last lecture before we truly open the can of worms. Okay. And we'll talk about these material properties. And fatigue limit is it's not something you measure as a material property. You get it from a plot similar to yield stress and ultimate stress. And so we'll talk about sort of the initiation of cracks, which properties control that, and then crack propagation, and different types of sort of ultimate failure. Right? We talked briefly about plastic collapse. Right? So not just a local part of the component will fail, but through the thickness, the whole thing collapses in some sense. And then when we talk about fatigue failures, we can have sort of crack propagation to failure, right? Or we can have very slow buildup of damage where the crack propagates very slowly. So we can have fast or slow crack propagation, and that's what would lead to sort of a catastrophic failure. And so we're going to keep putting together the pieces from materials through stresses, apply a failure criterion, and then either analyze a system or predict something about a system in the future. All right, so we do have to cover static failure theories, just so that everyone's on the same page. In case you don't remember something about them, that's what this lecture is going to be about. So we talked before about a tensile test, right? We take sort of an element that's a dog bone sample. Right, and we pull on it, measure the gauge length between 2 points, and then we apply some load. We know the area, initial area, we measure the gauge length again, and then we keep pulling on this thing until it breaks. And so that's good for uniaxial stress states, because all we have to do is apply the same situation to our component. But oftentimes we would have a complex stress state like we've been calculating. So we don't just have one tensile stress or shear stress. We could have all 6 components, right, that define a stress state. And so we need to figure out how those complex stress states can compare to this uniaxial situation such that we can predict when they will yield. And so it's pretty useful. I told you before about the octahedral stress and how that was used as a yield criterion. We're going to start with the simpler one today, the one that we did not apply to our pressure vessel, but we'll do a quick calculation in the middle of the class to compare this yield theory to the one that we used before. And so this first yield stress theory, right, is the maximum shear stress theory. And this makes a lot of sense because we know that materials, ductile metals, when we fracture them, they break in a 45-degree angle. And we also calculated that if we have a uniaxial test, then our maximum shear stress occurs at 45 degrees to that. So that's why this theory is based on maximum shear stress. It's also called sometimes the Tresca failure criterion because it's named after a person. So you might see that terminology. And this is used for ductile metals. And it's the most conservative theory. And we'll show why that is graphically, but I'm just going to write it down now. Okay. So we're going to state the theory as follows. Yielding is predicted when maximum shear stress in a stress element, right? So I'm going to call that tau max, exceeds the yield stress divided by 2. All right, and we can call that like a failure shear stress also. All right, so I sort of already explained it, that our tau max is defined as the difference between the maximum and minimum principal stresses, right? Sigma 3 minus sigma 1 divided by 2. If we have a uniaxial case, right, then that simplifies down because we only have sigma, sorry, those indices should be flipped. Okay. We only have sigma 1. And so then our tau max is simply sigma 1 divided by 2. Right? So in a uniaxial case, we compare sigma 1 divided by 2 to the yield stress divided by 2. And if that happens, we would predict yield. Okay. We can also incorporate a factor of safety into that. Right. So factors of safety, we'll call them like lowercase n. And so for a factor of safety, we have the sort of value we're comparing to, right? Our anchor value is a material property or criterion. And then we have what we measured underneath it. And so what we measured should be, if it's like a maximum stress we're applying to something, shouldn't be as high as the failure criterion. So that means if n is greater than or equal to 1, we would predict safety, or we would predict no yielding. You know from experience, factors of safety are often 2 or higher, but this is what we call a factor of safety. So that's if we consider a uniaxial case, and it's very simple to apply this. But what if we have a biaxial stress state where we don't have only sigma 1, but maybe sigma 1 and sigma 2? So I'll go to the next slide. So if we have a biaxial stress state, right, I'm going to draw it as sigma x, sigma y, and then we would have the corresponding ones because this is under static equilibrium. And then we also have tau xy on all the planes all around. So we have a biaxial stress state, or we can also call this plane stress because all the stresses are in a plane. And so if we do that, now we're no longer in a uniaxial stress state, and we might in fact have a combination of stresses in order to calculate this maximum shear stress. Right? So if we have a stress state like this, we can define right? We can come out with principal stresses, sigma 1 and sigma 2. Right? And for in this situation, we can draw this for any combination. But in this case, if we always have sigma 1 greater than sigma 2, right, greater than sigma 3, then we can just think about the maximum here. So we can say that the magnitude of the difference, I'm going to make that a 0. Hang on one second. I'm not going to make it a 0. Hang on. So if we have the magnitude of the difference of principal stresses greater than or equal to the magnitude of some failure stress, we can also state the state this failure criterion like that for a biaxial stress state. And then if we make a plot of sigma 1 versus sigma 2, then we can talk about how these are combined to get this failure criterion. So if we only have, let's talk about the uniaxial case. If we only have sigma 1, we're only along this x-axis. And so we can say that if that sigma 1 divided by 2 is greater than the yield stress divided by 2, then the component will fail. The same is true in the opposite sense, because the magnitude of that will still be, so in compression, will still happen, right? So that means anything along this x-axis, right, we would predict that it's safe inside there. If we go outside of those extremes, then we would predict yielding. Okay, so if that's what happens for sigma 1, if we also had if we had a stress state in sigma 2 that was similar, we could also draw those dots here. If we only had sort of sigma 2, if we imagine that, then it's safe all along that axis as well. So that's fine. But what if we have a combination? Right. Well, if both of these are positive, right, then we only have to consider one of them, the maximum one. And the other stress is always 0. So this was like if you were doing a prior class and you came up with like, hang on a second. Let me erase that. Okay. So if you were in a prior class and you came up with like a Moore's circle like this, and you would say, okay, I got my Moore's circle, I know the maximum shear stress, you know, it's this radius here, and then your professor said, no, 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 it's actually a 3D stress state. Don't forget to consider 0, right? So we're out here. So our real Moore's circle that has the maximum is way out here, okay? And so that's what happens if you have both of these are positive. So if both are positive, we can actually combine them, and they don't affect each other really when we're talking about the failure criterion. So we could draw a box like that, which is safe inside the box. Same thing happens if they are both compressive. We have 0 as the third principal stress, so we can draw a box this way, safe in here. Okay, very good. But where we start running into issues is if we have, if we're not in quadrant 1 or 3, but if we're in 2 or 4, where these have opposite signs from the other one. And that's where we have to combine them in order to get an effective stress state, right? And the way we combine them is we take their, we take the difference and divide by 2 to get a maximum shear stress. And so that is represented by these lines here. Yeah. And so inside this shape is the safe zone between, in a biaxial stress state for sigma 1 and sigma 2, if we consider that in some areas of this, the third principal stress is 0, and some it's not. Okay, so this is kind of a help for if you're a visual person to sort of imagine this. And then you can also find, if you go and look in the literature, you can find where people have taken data, right? So this is not just theoretical, but rather you can find experiments that fall generally near these curves like this that sort of confirm that this is more conservative. So those data points, I just put dots around the outside. Those, that this theory is a little bit more conservative, and that the actual measured data falls slightly outside of it, but in general, it can describe the shape. Okay. So then we have to think our last thought about a triaxial stress state, where not only do we have sigma 1, sigma 2, and maybe sigma 3 that's 0, but now we have all of them, and they could all have positive and negative values. So how do we expand this failure envelope from a little biaxial stress state like this to a triaxial stress state, or a stress state in 3D? Well, we do that by expanding it along another axis. So we take our same axes that we had, and I'm going to draw them a little bit differently this time. So we'll have sigma 1 coming out this way, and sigma 2 coming out this way. Okay. And so if these are the positive axes, then I could draw my shape. So that would be the box in quadrant 1. And I could draw sort of a corresponding box in quadrant 4. Right, those are safe. And then I connect the dots here, right, to sort of make this safety envelope. And we have sigma 1, sigma 2 on those axes, so sigma 3 is going to be more of a vertical axis. All right. And so now we have 3 axes here, and you might think, well, we just take this shape and then this sort of hexagon we have, and then just move it up and down, right? But that's not true, because if sigma 3 is positive, and if we have our maximum shear stress as sigma 1 minus sigma 3 divided by 2, then we're going to have another slope on there, and you can't just have a safe zone that's straight up from that plane. Okay? And so what actually happens is that this thing comes out at an angle that's related to the direction cosines of what you're looking at. Okay, so there's a figure in the book here that is much better to look at than a hand-drawn figure in class. And so it's figure 6.2, graphical representation of the maximum shearing stress theory for a general multi-axial state of stress. Wow, I drew that hexagon really poorly. Hang on one second. Well, I guess it's okay. So if we take sort of an angle that's arbitrary, but it's defined by our direction cosines, or our directional angles in this case, alpha, beta, and gamma, then our hexagon shape sort of moves up and down along that. So here's my crazy drawing of that. All right. So you should definitely look in the textbook for a much better drawing of this. And so that's our safety envelope in 3D. And anything outside of that, we would predict yielding. Okay. So that's the Tresca or maximum shear stress theory. The one that we applied the other day is I talked about the octahedral shear stress. Okay. And that comes from distortion energy failure theory. Where we're going to break up the strains and their corresponding stored energy into 2 different components. And we're going to say one of them contributes to yielding, and the other one doesn't. This originated from observations that ductile materials, so this is still for ductile materials, when subjected to a hydrostatic stress, they were much more resilient. They did not yield when they were predicted to yield. So a hydrostatic stress means that all the stresses are equal magnitude. All right. So they can be tensile or compressive, but if there is a hydrostatic stress state like this, it showed much higher, I guess, resistance to yield than expected. Okay, so this caused the mechanicians to go back to work. And specifically, those people were von Mises, who this is named after, and sometimes this is also called the von Mises-Hankey failure theory. And it theorizes that if the strain energy is divided into two parts, so one part, I'm just going to say strain energy is U, and so we're going to have two parts, and I'm going to call them V and D, because that's what the textbook says. This one is going to be the hydrostatic strain energy. And then this one is going to be a distortion energy. All right. So you can envision that there might be a stress state where it's not hydrostatic. You go ahead.
Does the V stand for volumetric and the D, I guess, distortion or
Mm-hmm.
toric?
We use those in
Yeah, the V might stand for volumetric, sure. And so if we have a stress state that's not a hydrostatic stress state, we can say that it is a hydrostatic stress state with something other, another stress state superimposed on it. So that would be a stress state that only relates to the distortion energy. So it kind of allows you to get rid of the small changes from just the hydrostatic stresses. Okay. So if I draw that up kind of in a form that we can understand, we could say that a 3D stress state, draw it as a box here, with 3 different stresses on it. All right, so these are all different stresses. That would be equal to a hydrostatic state where we have the same stress on all surfaces, and we're going to call that some sigma average, plus whatever is left over, which will distort the thing. So we can say that now our vertical stress would be sigma 2, whatever it was before, minus the sigma average. This would be sigma 3 minus the average. And then there's x over here on the side, or sorry, sigma 1. That's sigma 1 minus sigma average. So this third one is the one that is leading to yielding, whereas the hydrostatic stress state doesn't really lead to yielding. So let's see how we can calculate the energies for that. Okay. So if we have a stress-strain plot, and we're staying in the linear regime here, then we have a situation where we have a linear slope, and whoops, that should not be 1 over E. That should be just E. Where if we fit a slope to that line, the slope is the elastic modulus E. And the energy that is stored when this thing is elastically strained is the area of this triangle here. Right? And so we can say the area of that triangle is the strain energy, and I'll define that in a second, is 1/2 times, it's just the area of a triangle. So 1/2 times stress times strain. And then when we talk about the strain energies moving forward, they're all going to be per unit volume, and that's going to help the units to work out. Because we're always working with some kind of a volume that we're applying all these stresses to. So this is going to be energy per unit volume. So the units on that, right, energy is usually Newton meters, volume, meters cubed. So that comes out to be newtons per meter squared. So it comes out as a pressure unit, but what it really is a strain energy per unit volume. Okay. So for our stress cube, the total strain energy would be 1/2 of this triangle in all 3 dimensions. So sigma 1, epsilon 1 plus sigma 2, epsilon 2 plus sigma 3, epsilon 3. Okay. And so this is helpful, right? We've just described what the total strain energy is according to the stresses and strains in all dimensions. But we want to get this in terms of, let's say, a material property and only the stresses, because we're not going to we like to just use stresses and propagate that through rather than calculating all of the strains. So we're going to go back and use Hooke's law that we had written before. So one of those equations was epsilon 1 is sigma 1 divided by E minus Poisson ratio over E times sigma 2 plus sigma 3. This was our basis for saying that there can be strain in other directions besides the direction that stress is applied. And then we can write the same thing down for the different dimensions of strain here. And so we're going to combine these and put them into this equation. So we only have it in terms of stresses and elastic modulus. So I'll write that on the next slide. So here's our total strain energy per unit volume. So it's going to have a coefficient 1 divided by 2 times the elastic modulus, because that was in every term. And then we'll have some combination of terms here. So we'll have first principle stress, sigma 1 squared, sigma 2 squared, sigma 3 squared, and then we'll subtract off with a coefficient of minus 2 times the Poisson ratio, the combination of the stresses. The sum of the combination of the stresses. Okay. Whoops, sigma 3. Okay. So now we're going to define that average stress, that's our hydrostatic stress, and we'll see what happens when we subtract that out. So our average stress is just going to be the sum of the ones in all the directions divided by 3. So our hydrostatic stress. Okay. And so the hydrostatic stress is this stress average instead of sigma 1, sigma 2, sigma 3. So we plug that in for all of the stresses. Okay? And what we have is we come out with a volumetric or hydrostatic strain energy, call it UV, right? We wanted to define that. And in this case, we have 1 minus 2 times Poisson ratio divided by 6 elastic modulus. And then if we put the stress average in, and then we calculate, let me just make sure that this is right. But we keep it in terms of all these stresses. So hang on, what? 1 second. So it looks the same, but it's a slightly different combination of terms. So we'll have sigma 1 squared plus sigma 2 squared plus sigma 3 squared plus 2 times all these combinations. Okay. If our total strain energy is this volumetric or hydrostatic strain energy plus the distortion strain energy, then our distortion strain energy is the difference between these two. So the total minus the volumetric. And so I'll write down an expression for that, which is 1 plus Poisson ratio divided by 3e. And then we'll have our difference of stresses here squared. So this is starting to look a little bit more familiar, right? For the maximum shear stress theory, we had just the maximum difference between our principal stresses, right? Sigma 1 minus sigma 3. And that's what we kind of based everything on, right? Now we have a combination of all of the differences together, right? So you can kind of get a hint as to how we're going to start combining these for our actual failure criterion. Okay. So we have to get a failure criterion. So we're going to apply this to a uniaxial tension test, see when that would yield, and then come back and see how these combine in order to get to that case. Okay. It's the same for the other yield criterion. So for a tensile test, right, we only have sigma 1, and at yield, so the other ones are 0, and at yield, right, we talked about how the maximum shear stress is equal to the yield stress divided by 2, or sigma 1 is equal to the yield stress. If we cross out all the terms with sigma 2 and 3 in the prior expression for the distortion energy, we come up with a very simple expression which only includes sigma 1 squared. And if so, then at yield, we'll put in this equation here. And so here's what we have. We have UD is equal to 1 plus nu divided by 3E times the yield stress squared. Sorry, I'm using different terminology for yield stress. I'm going to stick with sigma for now. Okay. Okay, so this is still all in terms of strain energy, okay? But we don't really want to calculate strain energy. We just want to calculate something that we know from the stresses, apply that. So what we're going to do is apply this simplified equation and equate that to the full expression for the distortion energy. Okay. So I'm going to write that here really quick. So distortion energy from the prior slide was this combination of all the principal stresses squared, 2 squared plus sigma 2 minus sigma 3 squared. Come on. And then all those divide by 2. Set that equivalent to our new expression for when yielding occurs. And then we can cross out the coefficient because that's the same for both. And this is our failure criterion now. We don't calculate any energies. We just have this effective stress, and we compare that effective stress to the yield stress. This left-hand side is the von Mises stress. All right. And so you may be familiar with calculating that. And so this is our second yield criterion. I want to stop briefly to talk about the calculations that we did in the last class. So in the last class, we had a pressure vessel, right, that was filled by some pressure. And we had a first principal stress that was the pressure times the nominal radius divided by nominal thickness. We had a second principal stress that was half of that. And then we did not have a stress in the radial direction. So that was 0. And we went through and we calculated that if we apply the this distortion energy theory, which I called octahedral stress, but it turns out to be very similar, if not exactly the same. We got a pressure to yield of 1,427 psi. So this was for, let's call this distortion energy theory. And so now if we apply the maximum shear stress theory, we can compare what happens. So maximum shear stress theory says that it will yield when tau max is greater than or equal to yield stress divided by 2. Nope, just yield stress. It's divided by 2 when we have the sigma 1, sigma 3. Okay, there we go. Okay. And we know our tau max because it's just sigma 1 divided by 2. So equals sigma 1 divided by 2. So that's P times R naught divided by 2 T naught. So we can solve for pressure here. So when the pressure exceeds yield stress times 2 tau naught divided by R naught. Let me just look at my calculations here. This is not correct. Hang on. Yes. Here? Yeah. That's what I had first, and then I erased it. Yes, it should be. So then if we have a 2 here, then the 2's cancel out. Yeah, it should just have no coefficient. Yep. You got it. Okay. So that's our yield criteria. And so we could calculate P greater than equal to, and we come out with 1,236 psi. So it dropped about 13%. It's 13% lower if we take the first value to be sort of the more correct one, the less conservative one. If we go and think back on how we calculated the pressure that you would have to keep pumping it up to get the plastic collapse, that was 1,455 psi. And that actually does not change, because for that we only used the plastic strains, and we only used the sort of how it gets the K and the N to calculate that. And so I don't believe that that would change. Okay. So I wanted to mention also briefly about octahedral stresses. So I had a little discussion with one of the students after class last time. And so we can get, this is according to the textbook, the same results as the distortion energy theory by looking at the octahedral stresses. Okay. So octahedral, right, means a shape with 8 sides, in this case a prism with 8 sides. Okay. So if we had our well, I'll draw it just as a cube. If we have our stress cube here, right, and we decide to cut off one of the corners. So I'm going to draw sort of a shape right here. All right, so it's a triangular shape. And this is kind of like what we did when we were talking about defining the stress states in the first place. So if we cut off that corner, and then we have that plane, and we define a stress coming out of that plane, that's the octahedral stress. And we can do this if we basically have a larger cube and we cut off all of the faces such that we're left with an octahedron. Then the octahedral stress is what is on each surface. So I'm just going to write the equation here. Okay. And then we take the square root, so I'll just write a square on that side. Okay. And then the theory says that yielding begins when the octahedral shear stress in some element exceeds the octahedral shear stress in a tension test specimen at failure, right? So we've been going back to all of these uniaxial tension tests. Right? And so we can go through sort of a similar procedure where we would, in a tension test, define the octahedral shear stress if we only had sigma 1. Right, which comes out to be square root of 2 divided by 3 times the yield stress. Okay, and so this would predict yielding when the full expression, right, up on the top exceeds this one. And if we simplify the 3's out, then we come up with a factor of 2 in there, which is the same as the distortion energy theory. So I'll write that equation here, difference of stresses divide by 2, right, greater than equal to yield stress. Okay. So if we put the distortion energy theory and our Tresca, our max shear stress theory together in 2D, this can be a helpful map. So before, in a biaxial stress situation, right, we had our shear stress theory like this. But I told you that the data fell mostly outside of that. And so if we now plot the distortion energy theory with 2 stresses like this, then it is an ovoid that sort of hits the same vertices that the outside shape has. Okay? And so this is more typical of data. And this is the distortion energy theory. And this one is the max shear stress, the one on the inside. And so you can see that the failure envelope for distortion energy is a little bit bigger. So this confirms the idea that the shear stress theory is slightly more conservative. Okay. So this was kind of just a review for defining static failure theories for ductile metals. And so you should have seen a lot of this before, and you should be able to apply it readily. We will have some homework problems on this. And if you have issues, then just go on the class discussion board and post them, and we'll see if we can't get it sorted out. Okay. So you should know them because we are going to move beyond them. So at the beginning of the next lecture, I'll talk about brittle materials, failure theories, and then we'll start talking about cyclic loading. So I'll end there for this lecture.